You know, sometimes the solution to our biggest, most complicated problems comes from the tiniest of places. We're always on the hunt for faster, smarter ways to solve these massive logistical puzzles. And a lot of the time, the best inspiration isn't in a supercomputer. It's right outside in the natural world.
Okay, let's jump right in with a simple example. Imagine you've got to make a delivery to 4 different cities. How do you figure out the absolute best route? With just 4 stops, you could probably sketch it out, right? Figure it out on a napkin in a couple of minutes. Pretty easy.
But what happens when that list goes from 4 cities to 400 cities? All of a sudden, that napkin sketch is totally useless. The number of possible routes just explodes. It's a number so huge that a modern computer could literally run for centuries trying to check every single possibility and still not find the answer. The problem basically becomes impossible.
So how in the world do you solve an impossible problem like that? Well, the answer is to look down, way down. The inspiration comes from an organism that's been solving these crazy complex routing problems for millions of years, all without a single computer, the humble ant.
And this gets us right to the core idea. See, ants are absolute masters at finding the shortest path from their nest to food, and they do it with this beautifully simple system of communication, the pheromone trail.
Let's see how this plays out. Right at the very beginning, let's call it t=0, a group of ants leaves the nest and comes to a fork in the road. Now, one path is shorter than the other, but they don't know that yet. So what do? They just split up. About half go one way and half go the other. And as each ant walks, it's leaving behind this little chemical trail.
Now here's the crucial part, and it's just pure and simple logic. The ants that happen to pick the shorter path are going to get to the food and get back to the nest a whole lot faster than the ants that took the long way around.
And this is where the magic happens, because that first group on the short path gets back sooner. They lay down a second layer of pheromones on that same path. So when the next wave of ants gets to that fork, one trail now smells stronger than the other, and naturally, more of them are going to follow the stronger scent. So the split isn't 50-50 anymore, it's more like 20 ants going down the short path and only 10 down the long one. This whole process just keeps repeating, and pretty soon, the entire colony is using the most efficient route. It's genius.
So, that's the biology, which is incredible. But how do we take that elegant system and turn it into a powerful computer algorithm? Let's get into the actual rules of the road for our virtual ants.
It really just boils down to 4 basic things. First, our ants move between different points, or nodes, on a map. Second, they decide where to go next based on the strength of a virtual pheromone trail. Third, each ant has to complete a full tour, visiting every single spot. That tour is one possible solution. And finally, after it's done, the ant reinforces the path it took by laying down its own pheromones. And guess what? Shorter paths get a stronger scent.
You know, there's a fantastic scientific name for this whole process. It's called stigmergy. It's just a fancy way of saying it's a type of indirect communication. The ants aren't talking to each other? No. Instead, they change their environment by leaving these pheromones, and it's that change that influences how all the other ants behave. It's a perfect example of smart behavior emerging from a decentralized group. Pretty cool, right?
So, you might be wondering, how does a virtual ant actually make a choice? Well, at every single fork in the road, it looks at 2 key things. First, the strength of the pheromone trail. That's kind of like following the wisdom of the crowd, but it also looks at the actual distance to the next city. I mean, a really close city is always tempting, even if its trail isn't the strongest. The algorithm really cleverly balances following what's worked in the past with taking a chance on a new, short step.
Okay, so theory is great, but let's make this real. We're going to take these rules and apply them back to our simple 4-city problem, which is a classic example of what's called the traveling salesperson problem. Let's follow just one of our virtual ants on its journey.
Okay, here they are, cities A, B, C, and D. The goal is simple. Find the shortest possible loop that visits each city just once. Let's trace the path of our very first little ant as it tries to figure this out.
So before a single ant even moves, the algorithm sets up some initial pheromone levels. You can see them here in the table. Think of it like a faint, pre-existing scent on all the roads that gives the first few ants some basic guidance so they're not just wandering around completely blind.
All right, our ant starts its trip. Let's say it's already been to cities B and C. Now, to make sure it doesn't just go in circles or visit the same city twice, it keeps a little list in its head called a tour memory. Right now, that memory is BC.
So the ant is sitting there at city C. Its memory tells it, nope, can't go back to B. So
What are its options? It can either go to city A or it can go to city D. Which one is it going to be?
Well, it does that little probability calculation we talked about, weighing the pheromone strength versus the distance for both paths, and based on those starting values, let's say it makes its choice and heads off to city D.
So after visiting D, there's only one city left to finish the tour. Its memory is now B, C, D. Once it visits that last city, the tour is officially complete. Now, and this is super important, only after it has a full solution does it get to go back and lay down its own pheromone trail to reinforce the exact path it just took.
Okay, so we've just followed one single ant, finding one possible solution. But you might be thinking, big deal. The real power here isn't in one ant. It's in the collective intelligence of the entire colony. I mean, let's be honest. The journey we just watched, it might be a good route, or it could be a really terrible one. A single ant can get unlucky, make a bad turn early on that messes up the whole trip. Its solution is just one data point.
The real magic happens when you unleash thousands of these virtual ants all at the same time. They're all exploring different paths all at once. And the ants that just happen to find shorter or better routes, well, they finish faster and they deposit stronger pheromone trails. This attracts more ants to those good paths, which makes them even stronger. It's this amazing feedback loop that lets the colony very, very quickly zero in on the best possible answer.
And this brings us right back to that key idea, stigmergy. There's no boss, there's no central planner telling everyone what to do. All of this intelligent collective problem solving just emerges from a bunch of simple individuals following simple rules and changing their environment.
And this isn't just some fun academic theory. Ant colony optimization is a serious tool that's being used right now to solve huge, real-world problems. We're talking logistics for delivery companies, routing data packets through the internet, and even tackling complex manufacturing schedules. So, the big takeaway here is pretty amazing. From the simple, decentralized actions of thousands of individuals, an incredibly smart, optimal solution can just appear. We started with what seemed like an impossibly complex problem, and we found the key to solving it in the behavior of tiny ants. It really makes you wonder, doesn't it? What other brilliant solutions to our biggest challenges are just hiding out there in the natural world, waiting for us to notice?